welcome back to part 3 for the 2018 exam. Question 8. Two blocks, A of mass 4 kilos and B of mass 1 kilo, are being pushed to the right on a smooth frictionless surface by a 40 Newton force, as shown in figure 10. Part A. Calculate the magnitude of the force on block B by block A. Show your working. Okay, so the magnitude of the force on block B by block A. Well, it's kind of tricky to figure out a force when all you're given is mass. So we're probably going to have to work out the acceleration of block B, and that'll tell us the force on block B, right? So how do we work out the acceleration on block B? Well, we're going to treat this whole thing as one object with a total mass of 4 plus 1, which is 5 kilos. Okay, so what can we do here? Well, we know that there's a 40 Newton force being applied on the system, I guess you could call it. It's a frictionless surface, so this 40 newtons here is the only force doing anything contributing to their motion. So we're going to just say that F equals ma, where m is the mass of the system. In this case, we've got 40 equals the mass of the system, which is 5 kilos, times the acceleration of the system. So the whole system is accelerating at 40 divided by 5, which is 8 meters per second squared. Now, because A is like pushed up against B, they're both accelerating at the same rate. So B is accelerating at 8 meters per second squared. And so now we know B's acceleration, we know B's mass, we should be able to work out the force acting on B. And the only force that's acting on B is the contact force from A, which is what we're required to find. So the force on B by A is equal to B's mass times B's acceleration, which is just 1 times 8, which is 8 newtons. Here we go. Part B, state the magnitude and the direction of the force on block A by block B. So block A pushes against block B this way, block B pushes against block A this way. This is an action-reaction pair under Newton's third law. So the direction is to the left, and because it's a Newton's third law action-reaction pair, the forces are equal in magnitude, so that's also 8 newtons. Okay, let's double check the exam report. Just bring it up. Here we go. Alright, so question 8a. Most people got nothing, probably because they didn't know that they had to start looking at the system rather than trying to just focus on one object straight away. So yep, basically did exactly what we did, and 8 newtons. Most common error was to apply F equals ma, but only to the 4 kilogram block, which gave an acceleration of 10. In part B, yes, 8 newtons to the left. So I find it interesting that 56% of people got question A wrong, but 61% got full marks. So the only reason you'd get 0% is if you didn't provide an answer, unless they were being consequential. So probably someone just wrote a number in here, and then if you wrote the same number here, you would have got consequential marks for that. So that's a good point to bring up at this stage as well. If you don't know what the answer is to a question, but subsequent parts of the question require you to use an answer that you've previously found, just make something up. Just put something in the box and then use that value for for the next part of the question, okay? Because most of the time they will give you consequential marks for that. So I'm pretty sure that's what's happening here, which is why 61% still managed to get 2 marks for that. Okay, let's move on to question 9. Alright, question 9. The spacecraft Juno has been put into orbit around Jupiter. The table below contains information about the planet Jupiter and the spacecraft Juno. Figure 11 shows gravitational field strength as a function of distance from the center of Jupiter. And we have some data here as well. Okay, so just make a note. This is a gravitational field strength versus distance graph. Okay, not a gravitational force versus distance graph. Okay, those are two different things, and we deal with each of those things in their own way. Part A, calculate the gravitational force acting on Juno by Jupiter when Juno is at a distance of 2 times 10 to the 8 meters from the center of Jupiter. Show you working. Pardon me. Okay, well, calculate the gravitational force acting on Juno. Here, this graph is giving us information about the gravitational field strength at a particular distance from the center of Jupiter. Now, if Juno is at that particular distance, actually, you know what? I think we can actually just use the data, to be honest. So if we're working out gravitational force, not big G, F equals big G times mass 1 times mass 2 over r squared, which we've got all that data, so we don't need to use the graph here. So we just got mass of Jupiter, mass of Juno, radius of Jupiter. We don't even need the radius of Jupiter because we're saying we're already at a distance from the center of Jupiter. That's what the r would be here. So if I plug all that in, let's see what we get. 6.67 times 10 to the negative 11 times mass of each of those things multiplied together. So 1.9 times 10 to the 27 times mass of Juno, which is 1,500, over 2 times 10 to the 8 squared. Just being careful to square the 2 as well. Right, calculator time. 6.67 times 10 to the negative 11 times 1.9 times 10 to the 27 times 1,500 over 2 times 10 to the 8 squared. 4,752 sounds nice. 4,752 newtons. Cool, so that was just a straightforward calculation question. Nothing too hard about that one. Part B, use the graph in figure 11 to estimate the magnitude of the change in gravitational potential energy of the spacecraft Juno as it moves from a distance of this to a distance of this from the center of Jupiter. Show you working. Okay, so it does say use the graph, so we have to use the graph. And it's saying if Juno is at this position and it moves to this position, what is the change in gravitational potential energy as it does so? Now, because this is a field strength versus distance graph, the change in gravitational potential energy is equal to the area under the graph between those two distances times the mass of Juno. Okay? If it was just a force versus distance graph, you wouldn't have to multiply by the mass of Juno. Alright, so our job is basically just to work out this area here. Look, we're going to count squares for this one because this part's probably a little bit too curved for me to use a trapezium formula. So we're going to count squares and then work out the area that way. So let's be careful. So 1, 2, 3, 4, 5, 6. Now, the way I sort of tend to do this is if the area is more than half, count it as a full square. If the area is less than half, don't count it as a square at all. Right? So this would be 1 square. This would be 1, 1, 1, 1, 1, 1. This one, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Look, rest of them, I'd say, would combine to be another full square. So we count the rest of them as another full square. And so we've got 14 squares there. So the area would be 14 squares times the area of one square, which is, so that's 1 times 1 times 10 to the 8. Don't forget that part. So 14 times 1 times 1 times 10 to the 8, which is just times 10 to the 8. And then times the mass of Juno, which is 1,500. I should just make a note that there was 14 squares, just so they know that you've counted them. And now if we multiply that together, oh, hang on, I've made a bit of a mistake, I think. No, yeah, that's half, not 1. So that will modify by just adding times 0.5 there. Alright, cool. Now let's bring up our calculator. So that's half of 14 is 7, so 7 times 10 to the 8 times 1,500. 1.05 times 10 to the 12. There you go. So be very careful when you're working out the area. Look, you probably could have gotten away with using a trapezium formula for that one. But sometimes it's just better to count the squares and do it that way. Let's see what the report says. So, question 9a. Now, they're saying that from the graph, the gravitational field strength is 3 newtons per kilo. Did the question say use the graph? Calculate the gravitational force acting on Juno by Jupiter when Juno is at a distance of that. But see, we didn't need to worry about the graph because all the data was here. So, I don't know why the report says to do it using the graph, because that's what they've done here. And then they said many students calculated the force using Newton's law of gravitation. Okay, well, it says both results were considered correct, so the way we've done it is fine. The second method was mathematically more complex, and errors in this method constituted the most common error for the question. Well, that's just people not being careful with their calculation. I mean, that's not a hard calculation to do. I guess it is true that if you look at a distance of 2 times 10 to the 8 here, straight away that gives you a gravitational field strength of 3. And so you just do 3 times 1,500. Yeah, sure, it's a more simple calculation, but I don't know. I don't see what the big deal is of using it this way. Anyway, part B. So we've got, the area under the graph between 2 times 10 to the 8 and 1 times 10 to the 8 is estimated around 14 squares. Each square is equal to, so that's the times half that we did here. Okay, times 0.5 times 10 to the 8 times 1. And then, multiply that all by 14 and then times the mass of Juno. And you've got the same answer. So, allowances were made for students estimating a different number of squares. So typically with questions like this, if you're trying to find area under a graph like this, there will be some leniency towards like the range of values that are accepted. So long as you're not making any stupid counting mistakes, you should be okay. Just make sure you're trying to be as careful as possible with your area. Alright, let's move on. It also says here, some students were also used a difference in gravitational potential energy approach using this formula and substituting the different G values and H values. This also led to the correct answer. So because we know the value of little g from the graph, gravitational potential energy at each of those heights is mgh, then yeah, I guess you could work out the change in gravitational potential energy that way. But the area method is the most appropriate method to use for questions like this. It does say a number of students approximated the area under the graph as a trapezium. The students were not awarded full marks as a trapezium if there's an overestimation of the area. So yeah, if you draw a straight line from there to there, you're probably adding another square and a half, maybe 2. That's probably too much outside of the range of accepted values for this question. Alright, let's keep going. Look at C. I didn't realize there was part C. Part C, Europa is a moon of Jupiter. It has a circular orbit of radius this around Jupiter. Calculate the period of Europa's orbit. Okay, so the formula that you should have on your cheat sheet is, what is it going to be? It's going to be R t squared, no, other way around. R cubed over t squared equals gm over 4 pi squared. Okay, I don't think this is on your formula sheet, the one that's supplied to you. I always forget this formula. But what it's doing is it's combining the gravitational field strength, which is basically acceleration due to gravity. Well, no, so gravitational field strength is from here, but that's equal to acceleration due to gravity, and because we're in circular motion, I'm basically equating this to this, okay? And if you do a bit of rearranging, you end up with the formula that I've got there. So that formula has the period here, and all you need to know is the radius of orbit and the mass of the thing you're orbiting, and that can give you the period. So that's what we're going to use here. So that's a good one to have on your formula sheet. So t equals, just some algebra here, so it's going to be the square root of 4 pi squared times r cubed over gm, square root of 4 pi squared times 6.7 times 10 to the 8 meters cubed over 6.67 times 10 to the negative 11 times the mass of Jupiter, which was 1.9 times 10 to the 27. Alright, calculator time. Square root of fraction 4 times pi squared times 6.7 times 10 to the 8 cubed over 6.67 times 10 to the negative 11 times 1.9 times 10 to the 27. I think I've typed everything right there. 306,000 seconds. Sure, why not? So 3.06 times 10 to the 5 seconds. There you go. Alright, double check our exam report. Yep, there you go. Same formula, same answer. It's a pretty standard kind of question, so most people got full marks for that. While most students realised that this question required a combination of Newton's law of gravitation and circular motion, many could not demonstrate a suitable formula and substitution. Forgetting to cube the radius was the most common mathematical error. So yeah, just make sure you're cubing that properly. Question 10. Members of the public can now pay to take the zero gravity flights in specially modified jet aeroplanes that fly at an altitude of 8,000 meters above Earth's surface. A typical trajectory is shown in figure 12. At the top of the flight, the trajectory can be modeled as the arc of a circle. Right, part A, calculate the radius of the arc that would give passengers zero gravity at the top of the flight if the jet is traveling at 180 meters per second show you're working. So when it says they would give passengers 0 gravity, it's not saying that gravity is non-existent. They should have used other wording here. They should have mentioned something like that would give passengers a feeling of apparent weightlessness, which is like, yeah, it's the more technical term I guess you might want to use. Weightlessness being what normal force they're feeling, and that normal force being equal to 0. So it's basically saying calculate the radius of the arc that would give the passengers 0 normal force at the top of the flight. Okay. Now this is basically one of those situations where this part here is modeled as a circle, and you're basically going over the top of the hump of a hill, right? And so if you think about the forces acting on the plane, or on the passengers in the plane at that point, you've got gravity pointing down, and you've got the normal force pointing up, okay? But we want the normal force to be 0 so that the passengers feel like they're just falling, right? So we want this Fn to be equal to 0, okay? So if we're in a circular path, that means our net force is going to be towards the center, which is down there somewhere. But the only force acting on us, if we're assuming that the normal force is going to be equal to 0 here, the only force acting on us is gravity. So gravity, we're going to have mg, force due to gravity, is equal to the net force in circular motion, which is mv squared on r. And so your m's cancel out. And the question is calculate the radius of the arc. So we're solving for r here. So r is equal to v squared over g. The speed of the plane is 180 squared, and g is, I'm guessing, 9.8. Okay, and calculator tells me that 180 squared over 9.8, 3,306, I'll say 3.3 times 10 to the 3, lots of 3's there. Cool. Now let's double check the exam report. Yep, so quite a well done question. They do the same thing that we did. They just got that formula out of thin air apparently. So maybe just, if you could see a circular question, vertical circular motion question like this, make sure you write down where your stuff comes from, just in case, because you're trying to show the examiner you know what you're talking about rather than just, you know, finding formulas all the time. The most common errors were mathematical, as most students who made an attempt knew the problem involved circular motion. Yeah. Alright. Part B. Is the force of gravity on a passenger 0 at the top of the flight? Explain what 0 gravity experience means. Okay, so like I was saying up here, I don't like the wording here, 0 gravity, because that implies that gravity is 0. They should have said weightlessness. So is the force of gravity on a passenger 0? No. Gravity is still, I'll say force of gravity is still present. Force of gravity is still present as it is required to turn the plane in a circular path. Okay, so that's the first part of the question. Explain what 0 gravity experience means. Okay, so 0 gravity experience means that the passengers experience free fall, or 0 zero apparent weightlessness, whatever you want to say. But yeah, so there you go. Now let's have a look at the solution. There you go. So students were required to state that the force of gravity is not zero, and that the zero gravity experience is due to the lack of contact or a normal reaction force. Yeah, that's what I've said. Okay. Whoa. That's weird. Okay. Everything's zoomed out. 1 second. Okay, there we go. Many students stated that the force of gravity was zero at the top. No. And then struggle to explain how that might occur. So gravity basically exists everywhere in the universe. You have to be like infinitely far away for it to be zero, or there just has to be nothing else in the universe for there to be zero gravity, but even that's problematic, but we won't go there. Others stated that if the gravitational force was still present, it would be very small, which is also incorrect. Okay, you've got to go very, 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 very far away from something for gravity to be zero, or basically zero. Number of students made reference to apparent weightlessness. It should be pointed out that apparent weightlessness is no longer part of the study design, and you should replace that term with zero normal force. Okay. Which is probably why they didn't put that in the wording here, but whatever. That's neither here nor there. Question 11. Figure 13 shows two speakers, A and B, facing each other. The speakers are connected to the same signal generator/amplifier, and the speakers are simultaneously producing the same 340 Hz sound. Cool. Take the speed of sound to be 340 meters per second. Calculate the wavelength of the sound. Alright, so this is 1 mark, straightforward question. Speed equals frequency times wavelength. So wavelength equals speed over frequency, which is 340 over 340, which is 1 meter. Easy. If we get that one wrong, then I don't know what else to do. B. A student stands in the center equidistant from speakers A and B. He then moves towards speaker B and experiences a sequence of loud and quiet regions. He stops at the second region of quietness. How far has the student moved from the center? Explain your reasoning. So he stops at the second region of quietness. Alright. So there are a number of ways to answer this question, but I think the easiest way is, so when you have a setup like this, okay, where you've got two sources of waves coming at you, and you're standing in the middle, alright, this is basically like a standing wave setup, okay, because a standing wave, remember, is you send a wave signal along, and then that wave signal gets reflected back along the same piece of string, and then the two waves interfere with each other and produce standing waves. Okay, that's exactly what's going to be happening here. Okay, you've got waves coming from either end that are going to interfere with each other. All right, so you're basically standing in the middle of a standing wave. Okay. Now, the thing about standing waves is that the standing wave that's formed has the same wavelength as the wave that is initially being sent along the medium, right? So here the wavelength we've found out to be 1. The standing wave itself would have a wavelength of 1 as well, okay, just due to the geometry of the situation. So here's what's happening, all right? Let me just draw a standing wave just in general, so over here. Okay, and we'll draw the envelope. Alright, so there's our standing wave. Alright, when we're standing in the middle, okay, we are standing at an antinode, obviously, because the sound is equidistant from us, so our path difference is 0. So we could just assume that we're standing at like one of these points here. Okay, now the wavelength of the standing wave, remember, is 1 meter, because the wavelength of the sound that's coming out of the speakers is also 1 meter. So from here to here, it's 1 wavelength, so that's 1 meter. Okay. The question says a student stands in the center equidistant from speakers A and B. And then he moves towards speaker B and experiences a sequence of loud and quiet regions, he stops at the second region of quietness. Okay, so basically we're starting our walk here, we're walking towards B, we're at a loud region right in the middle, and then we walk here and we reach a node, okay, quiet region. So how far have we walked? Well, that's a quarter of that whole wavelength there. So from there to there is 1 meter. And so from there to there is 0.25 meters. You walk another 0.25 meters, you end up at the next loud region. Okay. And then you walk another 2.5 meters and you end up at the next quiet region, so the second quiet region. So how far have we walked in total? That's 0.75 meters. Okay, so that's the answer. So we can write that in. Now to explain our reasoning, you just have to say in so many words that what we explained here. So yeah, I mean, I'm not going to write it down. You can just refer to the report and also just listen again to what I just said. Yeah, so the standing wave has a wavelength of 1 meter because that's the wavelength of the sound that's coming out of the speakers. And then, so if you walk to the second quiet region towards B, you've walked 3/4 of a full wavelength, or 0.75 meters. Okay. Have a look at the report. So part A, 92% got that one right. The other 8%, no idea what you guys were doing. 11B, students were required to identify that at the center there will be a region of relative loudness. So that's because you're equidistant and path difference is 0. That's what they said there. That's what you had to say. The first node or quiet region will be 1/4 wavelength from this position. That's what we've started explaining with the diagram. And the second node or quiet region will be 1/2 a wavelength further on from that, which the total length would be 0.75. So it was 3 marks. 1 mark, I guess, for the number, and then another 2 marks for explaining what was going on. So 1 mark, I guess, for the explanation would come from identifying that the center would be a loud region, and then the second mark would come from somehow explaining that the standing wave has a wavelength of 1 meter. The first quiet region happens at 1/4 of a wavelength. The next quiet region happens at 3/4 of the full wavelength. Okay, so that's your 3 marks there. Question 12. Optical fibers are constructed using transparent materials with different refractive indices. Figure 14 shows one type of optical fiber that has a cylindrical core and surrounding cladding. Laser light of wavelength 565 nanometers is shone from air into the optical fiber. Cool, so we're going from air into the core of the fiber, and then there's a cladding around it with different refractive indices. Calculate the frequency of the laser light before it enters the optical fiber. So this is, we're assuming light is a wave, so V equals frequency times wavelength, and the frequency is equal to the speed of the wave, which is the speed of light here, over the wavelength, which is 565 nanometers. Calculate a time. So 3e8 divided by 565e-9. 5.3, everything's got 3 significant figures, so we'll go 5.31 times 10 to the 14. Okay. Part B, calculate the critical angle for the laser light at the cladding core boundary. Show your working. So this just straight comes from your formula sheet, Snell's law. Got to be careful I don't scroll past it. There it is. Okay, so Snell's law, and at the critical angle is when your angle of refraction in theta 2 is 90 degrees. Okay, so if you just set that up and then solve for the first angle of incidence, then that's how we do it. Okay, so we've got n1 sine theta 1 equals n2 sine of 90 degrees. Okay. And then I said sine 1, not sine theta 1. Okay, so theta 1 is equal to, oh, by the way, this is just equals 1, sine of 90 degrees. And then so theta 1, your critical angle, is inverse sine of n2 over n1. Okay, so put a little subscript c for critical. Okay, so this formula itself should be on your reference sheet that you bring in yourself. Plug everything in. So n2 is where we're going, which is the cladding, so that's 1.45. And n1 is where we're coming from, which is the core, 1.67. And we get 60.3 degrees. Okay. Just be careful with your critical angle that you don't swap these two around, because then you'll get math error, because you can't take inverse sine of a number bigger than 1. This fraction in here has to be less than 1, or between 0 and 1. Alright. Part C, calculate the speed of the laser light once it enters the core of the optical fiber. Give your answer to correct to 3 significant figures. That's important, so we'll highlight that. Show you working. Alright, so calculate the speed of light. The speed of light does change depending on the medium you're going through. And once again, that comes from your formula sheet here, which is the other version of Snell's law, I guess, which relates the refractive indices with the speeds of light in those mediums. So n1 v1 equals n2 v2, so that's all we've got to write down. Okay, we're calculating v2 once we enter the core of the optical fiber, which is just n1 v1 over n2, which is, well, n1 is, we're coming from light, so it's 1. Speed of light in, sorry, we're coming from air. Speed of light in air is just 3 times 10 to the 8. And then n2, I think, was 1.67. Yep. Alright, calculator says 3e8 divided by 1.67. Right, let's go there. So it's 1.80 times 10 to the 8. I think, yeah. Move that 2 across, that becomes an 8. 1 point, for 3 significant figures, that 9 rounds up to a 0, and then the 7 rounds up to an 8. So it's 1.80. Make sure you include the 0, because that's part of your significant figures now, times 10 to the 8 meters per second. Alright, let's check our report. Okay, first one's good. Second one's good. Third one's good. Okay, there we go. Done. Question 13. Physics students studying interference set up a double slit experiment using a 610 nanometer laser as shown in figure 15. Alright, the light power output of the laser is this number. Calculate the number of photons leaving the laser each second. Show your working. Okay, so power, just remember, is energy over time. So basically what this is saying is that each second there is that many joules of energy being outputted by the laser. So to calculate the number of photons leaving the laser each second, we've got to work out the energy of one photon and then divide this number by that energy, and that will give us how many photons there are. So 610 nanometer laser. Oops. Alright, so the energy of a single photon is hc over lambda. You have to be careful to use the joules version of H because we're going to be using the joules version of energy. So 6.63 times 10 to the negative 34 times 3 times 10 to the 8 over 610 times 10 to the negative 9. Okay, so this is the energy of one photon. Calculate that. 6.63 times 10 to the negative 34 times 3 times 10 to the 8 over 610 times 10 to the negative 9. That looks alright. 3.26 times 10 to the negative 19. Alright, 3.26 times 10 to the negative 19. So that's the energy of a single photon. It's telling us this much energy is coming out of the laser every second. So we just divide this number by this number, and we get not E, N of photons, number of photons is equal to total energy divided by energy of a single photon. And we should get a big number because photons are tiny. 5.03 times 10 to the negative 3 over 3.26 times 10 to the negative 19. Here you go, 1.5 times 10 to the 16. There we go. No units because it's a number of stuff. Okay, check our answer. Yep, there you go. They've added an extra significant figure in there, that's okay. Yeah, so same idea, energy of a single photon, that's that. Total number is total energy divided by the energy of a single photon. You get the same answer. Cool. Alright, a section of the interference pattern is observed by the students shown in figure 16. There is a bright band at point C, the center point of the pattern, so that's there. Cool. Explain why point C is in a bright band rather than a dark band. Okay, so point C is in the center, so we say at the center that point is equidistant from each slit. Okay, and so therefore the path difference is equal to 0, so constructive interference occurs. Resulting in a bright band. I think that gets the point across. Let's double check the report. Alright, here we go. So, students were required to identify that the path difference to the point C is 0, and this results in constructive interference at C. Yeah, that's what we did. While most students were able to identify constructive interference as the mechanism for bright reason, reason? Maybe they meant region. They went on to explain interference in detail. Simply identifying constructive interference explains all bright regions and not the specific region. Students need to remember to focus on responding to the question asked. So yeah, don't waffle on. Right, get the point across as quick as you can. Why is point C a bright band and not a dark band? Because at point C, you're in the center, the path difference is 0, and constructive interference occurs when the path difference is 0. That's all you got to say. Part C. Another point on the pattern to the right of C is further from S1 than S2 by a distance of blah, blah, blah. Mark this point on figure 16 by writing an X above the point. You must use a calculation to justify your answer. Okay, so it says another point on the pattern to the right of C. Okay, so we're going to be marking one of these lines here. Alright. It says that that point, wherever it happens to be, is further from S1 than S2 by this distance. That is a roundabout way of saying the path difference to that particular point, wherever it happens to be here, the path difference is this number. Okay? So, using that knowledge, we basically know the path difference, and we know the wavelength of the light that's coming from the laser is this. So if I can work out how many wavelengths is my path difference, that will then tell me whether it's a bright band or a dark band, and also tell me which bright or dark band it is. So how many wavelengths is this path difference? So you just do the path difference divided by the wavelength, or just set this up first. So path difference, actually we don't have to do that. Just say 2.14 times 10 to the negative 6 divided by the wavelength. So this is telling me how many wavelengths fit into my path difference. And we're looking for either a whole number or something 0.5, right? Because that'll tell us if it's a bright band or a dark band. So the wavelength was 610 nanometers. Right, what do we get? 2.14 times 10 to the negative 6 over 610 times 10 to the negative 9. 3.5, so that's fine. 3.5. So the fact that it's a 0.5 means we are at a dark spot, and the formula for dark spots or nodes or nodal lines, whatever you want to call it, is n minus half times your wavelength. Okay, so this is telling me that n has to be 4, because 4 minus a half is 3.5. So we're at the fourth dark band, 1, 2, 3, 4, from the center, and we're talking about to the right of the center. So we're going to mark that point with X. Okay, and then you can say dark band, just to make sure that the examiner knows that you know what you're doing. Let's double check our answer. There it is. The path difference in terms of lambda is this, so that's what we did. 3.5 is 4 minus a half, so that's the fourth dark band from the center as shown. Some students who did not receive any marks showed no understanding of how to solve the problem. Thanks, examiner's report. You're very helpful. Let's move on. Question 14. Yani is stationary in a spaceship traveling at constant speed. Does this mean that the spaceship must be in an inertial frame of reference? Justify your answer. Okay, so at first glance, the immediate thing that came to my mind is yes. However, it says constant speed, not constant velocity. So, you can have a constant speed while still being in a non-inertial reference frame if you're traveling in a circular path at a constant speed. So, inertial reference frame implies that it's zero acceleration. So just make a note of that. Inertial implies acceleration equals 0. Okay. Yani could be traveling in a uniform circular path which would mean that acceleration is not 0. So constant speed does not imply inertial reference frame. Okay, there's probably a much better way to word that, but you're basically trying to get the idea across that constant speed doesn't mean constant velocity. Constant velocity means acceleration is 0. Constant speed just means it's a constant speed. So acceleration could still be non-zero, especially if you're traveling in a circle. Let's see what the report suggests. Students were required to identify that constant speed is not the same as constant velocity. Yep, cool, that's what we did. And that the ship in question could be traveling in a circular path, or it could be in orbit and still be traveling at a constant speed. Therefore, the spaceship may not be in an inertial frame of reference. That's exactly what we said. This question was not answered well, and it appears that further improvement is required in the area of special relativity. Many students made statements such as Gianni is in an inertial reference frame, but the spaceship is not, which makes no sense. Alright. Question 15. A stationary scientist in an inertial reference frame observes a spaceship moving past her at a constant velocity. She notes that the clocks on the spaceship, which are operating normally, run 8 times slower than her clocks, which are also operating normally. The spaceship has a mass of 10,000 kilograms. Calculate the kinetic energy of the spaceship in the scientist frame of reference. Show your working. So we've got information about like how fast the clocks are running relative to one another. So put yourself in the scientist frame of reference. Okay, you are the scientist now. You watch a ship go past you. Okay, in your mind, your clock runs at a normal speed because this clock is with you. So you would call that your own time. But you note that the time it takes for, let's say, 1 second to pass on the ship that's moving past you, it would take 8 seconds of your own time. Okay, so that means your time. No, so how do I put this? It means that the time taken for things to happen from your reference frame, the scientist reference frame, when measuring how long a similar thing would happen in your the spaceship traveling past you's reference frame, that time has been dilated. Okay, so let's set it up like this. Just imagine, just ask yourself the question: how much of my own time does it take for the other person's time to tick 1 second? Okay, your clock would take 8 seconds for every 1 second that ticks on the spaceship's clock, because that's what this statement here says. Okay, so we have the following equation: T equals gamma times T0. Okay, T and T0 differ in their size, so T is always going to be a bigger value than T0, and so that should give you a hint as to which number should go where. So I'm always thinking about how much time passes for each clock when you're talking about just being one of the observers. So in this case, we're the scientist. So let's compare how much time passes on each clock for whatever period of time you would like to talk about. So 1 second on the spaceship's clock takes 8 seconds of our own time to pass. So this is an 8, and you've got gamma times 1, which implies that gamma equals 8. Okay, cool. Hopefully that made some sense. I know I jumbled my words a little bit there, but that's just how I think about it. And setting up your time dilation equations, they're always somewhat tricky because it's very easy to get the two values confused. But now that we've got the value of gamma, we can now work out the kinetic energy, because that's the actual question. So calculate the kinetic energy. So from your formula sheet, you get kinetic energy, relativistic kinetic energy, is equal to gamma minus 1 times I'll say m0 c squared, where m0 is the rest mass of the spaceship, so 10,000 kilograms. Yeah. Right, so this is just going to be 7, because 8 minus 1, times 10,000 mass of the spaceship, times speed of light squared, 3 times 10 to the 8 in brackets, squared. Right, what do we get? So it's 70,000 squared, 6.3 times 10 to the 21. Joules. Okay, let's check our report. Okay, so gamma equals 8 from the phrase runs 8 times slower. Okay, just always keeping in the back of your mind, gamma has to be 1 or more. It can't be something that's less than 1. So the phrase runs 8 times slower. The key word there is 8. Okay, so it can't be 1 over 8. So it has to be 8. Yeah. So gamma is 8, and then you plug it into your E equals gamma minus 1 mc squared equation. So the formula sheet, that has it down somewhere. This one, there you go, relativistic kinetic energy. Easy. Alright. Question 16. Quasars are amongst the most distant and brightest objects in the universe. One quasar has a brightness that changes rapidly with time. Scientists observe the quasar's brightness over a 20-hour time interval in the Earth's frame of reference. The quasar is moving away from Earth at this speed and this Lorentz factor. Calculate the time interval that would be observed in the quasar's frame of reference. Show you're working. So imagine you have a clock and your friend goes to this quasar and also has the same clock. Because you are standing on Earth and this quasar and friend are moving away from you, your friend's clock would run more slowly, so less time would pass for them. So our time that we measure is t. The time that they measure would be t0. So let's set that up. T equals gamma t0. And our job is to work out what t0 is. Okay, because our time interval is 20 hours on Earth. So 20 hours, because our answer is expressed in hours, we don't have to do any change of unit here. So I'll just do 20 equals, and gamma is 1.41 times t0, and so therefore t0 is equal to 20 over 1.41, which is 14.2. Oops. 14.2 hours. Alright, let's check the report. Yep, there you go, 14.2. The most common error was to confuse proper time with dilated time, which resulted in multiplying 20 by 1.41. So again, always just think to yourself, whose clock is running more slowly? That person is typically the one who's measuring the proper time. Okay? Because if you're on Earth, you're measuring the time not for something to happen on our end, you're measuring how long it takes for something to happen in someone else's reference frame. So we're measuring the dilated time. The person over there is going to be measuring their own proper time. Question 17. To investigate the photoelectric effects, Sai and Kim set up an experiment. The apparatus is shown here. Typical setup. With the light source on and a filter in place, Sai and Kim measure the maximum kinetic energy of emitted photoelectrons by gradually changing the collector voltage until the current measured by the ammeter just falls to 0. They record this voltage, the stopping voltage, so that's here, for each frequency of the incident light. So they change the frequency. They've got some results here, and plot their results in the graph of stopping voltage versus frequency. That's this. With 6 times 10 to the 14 Hertz light, the ammeter always shows 0. Kai wants to repeat the experiment for this frequency with a much brighter light source and wants to expose the metal to the light for much longer. Kim says photoelectrons will never be ejected with this frequency of light. Who is correct? Sai or Kim? Write the name in the box provided below. Okay, so it's saying this frequency of light, the ammeter is 0, which means no photoelectrons are being ejected, probably because this is below the threshold frequency. Okay, so no matter how bright that light is, photoelectrons will never get ejected, and so you'll never detect a current, which means that Kim is correct. No explanation required, just write a name, 50-50. There you go. Now part 2 though, what explanation might Psi give to support her opinion that by waiting longer and using a brighter light source, photoelectrons could be ejected from the metal with a lighter frequency of that? So what explanation might Psi give, okay, the wrong person, or the person who's wrong, what explanation could they possibly give to support the claim that the photoelectrons could be ejected from the metal by waiting longer and using a brighter light source? Well, Psi might be thinking in terms of the wave model, right? So Psi might say, under the wave model, according to a wave model, okay, brightness is a measure of light energy. By leaving the light shining on the metal, energy would eventually build up enough to eject electrons. Okay, so again, according to a wave model, brightness is a measure of light's energy. By leaving the light shining on the metal, energy would eventually build up enough to eject the electrons. So the idea is that, yeah, the brighter the light is, or the longer that you leave it shining on the metal, then eventually you'll build up enough energy to eject the electrons, according to a wave model. Okay, it's very important that you say according to a wave model. So let's have a read of the report. So part A, Kim is correct, good, 78% got that right. This question here, this question assessed students' understanding of the wave model predictions of the photoelectric effect. Many students identified that Psi was referring to the wave model, that they were not required to do so. Oh, okay. Students were required to identify that increasing the brightness would increase the amplitude and energy of the light, and that by combining this with a longer exposure time would increase the total energy delivered to the metal. If more energy was delivered, then the electrons may be able to accumulate enough energy to be ejected. Students who received only 1 mark were able to state that the energy delivered would be increased, but could not relate this to both the change in brightness and the increase in time. Students who did not receive any marks generally tried to apply a particle model explanation with no success. So I find it interesting that they said students identified that Psi was referring to the wave model, though they were not required to do so. But if you didn't specify that you're talking about a wave model, then, I mean, this doesn't make much sense, because the energy, I guess the build-up of energy is not really a wave model thing. So that's probably why you don't have to specify wave model. But yeah, just identifying that the brightness measures the light's energy, and then by increasing the amount of energy that's shining on the metal, or how much energy is provided to the metal, we should say, then eventually the energy would build up enough to eject those electrons. Cool. Alright. Part B. Use the graph to calculate Planck's constant, show your working. Alright, so according to our graph, we need to work out Planck's constant. So I guess the first thing we need to do is draw a line of best fit. Now, it's very hard for me to draw my line of best fit because I'm just using a stylus on the screen. I guess I can try and do a straight line. I might just pause here and I'll draw the line of best fit myself, and then we can talk about it. So you'll see some things magically appear on the screen in a second. Alright, so that's the best I could do with the technology available to me. But I guess now we can say that, okay, well, our job is to work out the Planck's constant. So we've got this line of best fit. Now we just have to pick some points that we believe to be on the line. So that looks like a nice point there. So we'll just describe that point. So that is 6 times 10 to the 14 comma negative 0.5. Another point that we might like to use, maybe I'll go for this one. So that would be 1 times 10 to the 14, and we'll say that's negative 3.25. Yeah, that looks good. Alright. So you had to have drawn a line of best fit, identified 2 points on the line, and now we have to use the graph. So the gradient would give you Planck's constant. Okay, so for our gradient, we've got rise over run. So the rise would be negative 0.5 minus negative 3.25, or negative 0.5 plus 3.25 over the run, which is 6 times 10 to the 14 minus 1 times 10 to the 14, so 5 times 10 to the 14. But I'll put the points in, so 6 times 10 to the 14 minus 1 times 10 to the 14. This is just an estimate. Everyone's going to have different lines of best fit, so there will be tolerance in the answer. Right, so 3.25 minus 0.5 is 2.75 divided by 5 times 10 to the 14. 5.5 times 10 to the negative 15. So hopefully that's good enough as a response, and that's in electron volts per second. The reason is the graph is volts versus frequency. Anytime you have volts here, Planck's constant is going to be the electron volt version. If this was energy, you've got 2 options for energy. Energy could be expressed as electron volts or joules. Obviously, if this is electron volts, then Planck's constant is the electron volts version. If the energy here is joules for whatever reason, then your Planck's constant would be in joule seconds. Alright, so 5.5 times 10 to the negative 15. Let's have a look at the report. Here we go. Students were required to identify Planck's constant can be found from the gradient. Yep, did that. Right, and then we actually went ahead and did the gradient calculation. So depending on everyone's points, everyone's got different lines. Here it says that the correct response was given within the range 5 to 6 times 10 to the negative 15, so we're bang right in the middle. Yeah, so have a read of this, pause video, and we'll just do the next one. Part C. Determine the work function of the metal from the graph. Give your reasoning. Okay, so back up at our line of best fit. You just have to remember, this is just knowledge, that the y coordinate, or rather the negative of the y, not y coordinate, y intercept, the negative of the y intercept gives you the work function. Okay. In this case, our line of best fit looks like it goes to negative 3.75. Okay. So I'm going to claim that the work function equals the negative y-intercept, which is equal to 3.75. Okay, don't include the negative in your answer. Okay, work function is a measurement of energy. Energy is not negative. It's just the magnitude of that number. All right. So let's look at our report. Here we go. Using the graph, you get the work function is around 3.5 with a tolerance of 0.5 up or down to allow for variations in how you drew your line of best fit. So for us, it's 3.75, still within the tolerance. So we're all good. significant number of students responded by saying that the work function comes from this formula. No, the work function doesn't come from that formula. The work function is just a value that depends on the material you're using, but it is true that the work function and threshold frequency are related using that formula, but then you still need to be able to tell me what the threshold frequency is. So you're sort of double handling a little bit there. If you've got your line of best fit, this tells you the work function straight away. Where am I? Yeah, if you did this, it looks like they're saying that a number of students just use the value of the Planck's constant from the formula sheet. That would give you a different work function here, because the Planck's constant that we determined from the graph is not 4.14 times 10 to the negative 15. So use the values on the graph, or the values related to the graph, when answering questions like this. Question 18. The diffraction patterns for X-rays and electrons through thin polycrystalline aluminium foil have been combined in the diagram in figure 18, which shows an electron diffraction pattern on the left and an X-ray diffraction pattern on the right. The images are to the same scale. The X-rays have a photon energy of 8,000 electron volts. Part A, calculate the wavelength of the electrons in nanometers, show your working. Okay, wavelength of the electrons. Now, you can very clearly see that because the images are to the same scale, then the spacing between the diffraction patterns for both electrons and X-rays are the same. So the photons have a particular energy, and we could work out their wavelength or their momentum from that. And then it would be true that because the spacing is the same, that the electrons have the same momentum or wavelength. So I think we'll go the wavelength route. So the wavelength of the photons, if they have that particular energy, so we have the following formula, E equals, so energy of a photon equals hc on lambda. So the wavelength is hc on energy. Now, any time you're using this kind of formula, we need to use we don't have to use the Joule's version of H, because the energy is in electron volts, so that's fine. So we use 4.14 times 10 to the negative 15 times the speed of light divided by the energy of the photons, which is 8,000. And so the wavelength of the photons, let's work that out, so 4.14 times 10 to the negative 15 times 3 times 10 to the 8 over 8,000, 1.55 times 10 to the negative 10 meters. Be careful, the unit in the box is nanometers, so we have to convert this to nanometers, and you just have to be careful, we're 1 power of 10 away from negative 9, so this is a smaller number than times 10 to the negative 9, so it's 0.155 times 10 to the negative 9. We can kind of do that on the calculator. If I press shift engineering, it just goes to the next biggest power of multiple of 3. So that's 0.155 times 10 to the negative 9. There's your nanometers. So it's 0.155. Okay. You might want to be careful and just specify that the wavelength of the electrons is equal to the wavelength of the photons due to same spacing. Just to make it clear you know what you're doing. Alright, the report. Okay, electron and X-ray must have the same wavelength if they produce the same diffraction pattern, so we said that. Then it's just the calculation. There you go. Part B. Calculate the kinetic energy of the electrons in joules, show you working. Alright, the kinetic energy of the electrons. So, here it's 3 marks, so there's a bit of working out involved. So let's think about where we might start. Now, we know the wavelength of the electrons, the de Broglie wavelength. The de Broglie wavelength formula is, where is it? Here, okay? So the de Broglie wavelength allows us to work out the momentum of these electrons, right? So we can do that, and then using the momentum, I could then throw that into a, well, technically I could find the velocity of those electrons if I knew their momentum, and then from the velocity I could work out their kinetic energy. But there's a nice formula that relates momentum with kinetic energy that you should have on your cheat sheets, but I'll show you how to get that anyway. So first let's work out the momentum of those electrons. So momentum is h over de Broglie wavelength. This formula works for both electrons and photons. So we have to use the joules version of h if you're doing this formula. So 6.63 times 10 to the negative 34 over the wavelength, which is 0.155 times 10 to the negative 9. Okay, 6.63 times 10 to the negative 34 over 0.155 times 10 to the negative 9. So that's our wavelength, 4.28. Let's go. Actually, I might use one extra significant figure, so 4.277. No, not 2. 4.277 times 10 to the, it was negative 24, double check quickly. Right, cool. So, that's the momentum. Now, the formula for kinetic energy in terms of momentum is P, now I've got to be sure I'm doing it right, I think it's P squared over 2m. Now, let's just see where this comes from quickly. So, kinetic energy is half mv squared. Okay, if I multiply this by m over m, okay, which is basically 1, I get m squared v squared over 2m, and momentum is m times v, so on the top I've got m times v squared, which is just p squared. Okay, so that's how you get your modified kinetic energy formula. So we can just chuck our momentum straight into that without calculating the velocity, so 4.277 times 10 to the negative 24 squared, and this is talking about the electrons, so the mass of an electron is 9.1 times 10 to the negative 31, which gives us, I'll just square that because I've rounded it here, but if it's on my calculator, I'll just square it. So that squared over 2 times the mass of the electron. Yep, 1 times 10 to the negative 17. There we go. Right, so let's double check that I've done it properly. Alright, so there we go, there's the wavelength of your electrons from part A. Yeah, we talked about that. Part B is, there we go, yep, perfect. Majority of students struggle to begin responding. There are a range of incorrect formulas used as a starting point with no progress beyond. Yeah, well, you just got to see these questions before you know how to do them, basically, which is what you studied for. Right. How much more do we have? Is the last one? Yes, the last one. Alright, question 19. Figure 19 shows the spectrum of light emitted from a hydrogen vapor lamp. The spectral line indicated by the arrow on figure 19 is the visible region of the spectrum. The following list gives the 4 visible colors that are emitted by the hydrogen atom. Circle the color that corresponds to the spectral line indicated by this arrow on figure 19. Okay, so on your cheat sheet you should have like a diagram of like the electromagnetic spectrum, and the visible light part you should have a note that says it starts at around 400 nanometers, that's violet light, and then up to 700 nanometers, that's red light. So because this is more towards the red end of the spectrum, this arrow, I'm just going to say red. There we go. Explain why the visible spectrum of light emitted from a hydrogen vapor lamp gives discrete spectral lines. Okay, so I'm going to refer you to the study design, not study design, the report here, because I can't be bothered writing it all down. But basically, we're going to talk about, so it's very boldly saying discrete. So we're going to be talking about the fact that there are discrete energy levels inside your hydrogen atoms that the electrons can jump between. Okay, now an energy level can only exist if the electron orbiting at that energy, if the circumference of the electron's orbit is an integer multiple of the electron's de Broglie wavelength. And that's important because if it's an integer multiple of the electron's de Broglie wavelength, then the electron's wave will constructively interfere with itself and will form a stable standing wave at that orbit, contributing to the stable energy level. Okay, if it doesn't have that condition that the circumference of the orbit is an integer multiple of its de Broglie wavelength, it's just going to destructively interfere and it will cease to exist. So it's not an allowable energy level. So that's why we have discrete energy levels rather than a continuous, I guess, range of energy levels. So let's just have a look at the report. Okay, so electrons orbit nuclei in shells with discrete energy levels. Electrons can transition between these shells by absorbing or emitting. Oh, I didn't even, okay. No, that makes sense. Okay, so electrons orbit nuclei in shells with discrete energy levels. Electrons can transition between these shells by absorbing or emitting discrete amounts of energy equal to the difference between the two shells. Since transitioning electrons can only release discrete amounts of energy, only discrete spectral lines will be observed. Okay, so I waffled on too much because it's not asking for the reason why discrete energy levels exist. It's just saying why there are only certain lines and not like a continuous range of lines. So it just went, let's see it again. Point 1, electrons orbit in shells, or you could even say at different radii. Electrons can transition between these shells by absorbing or emitting discrete amounts of energy. In this case, emitting when they go down an energy shell. Since transitioning electrons can only release discrete amounts of energy, only discrete spectral lines will be observed. So that's equal to the jump, the energy level difference between the two orbits, right? You don't have to talk about why those discrete energy levels exist. That's when you go on to talk about the de Broglie wavelength, okay? But that's not what the question's asking, and that was my error there. Okay. Alright, last one, question 20. Some students have collected data on the orbital period T and orbital radius R of 5 of Saturn's moons. The results are shown in the table below. Assume that the moons are in circular orbits. Okay, so there's a bunch of data here. Alright, on the axis provided below, plot a graph of the data T squared versus R cubed. Include a scale on each axis, draw a line of best fit. 5 marks, so just make sure we're being very careful. I'm going to pause and you'll see some things magically appear on the screen, and then we'll talk about it. Alright, there we go. So let's see what I've done. Plot a graph of the observational data T squared versus R cubed. Include a scale in each axis, draw a line of best fit. So the scale and units first. So your T squared is times 10 to the 10, so put that in there. Your R cubed is times 10 to the 24, so you put that in there. Now look at the range of your data, so it goes up to, like, okay, the next whole number would be 16. So I've counted, and that goes up to 17, so that's 16, that I'll call that 15. And then each 5 is just 5 units. This one, your data goes from like 0 to 150. So again, you count it across, 150 lands here, and then you just break everything up nicely into that. Okay. All right. Your data itself, you just have to be very careful. Use a ruler to line things up, so it should look something like this. And then your line of best fit, some points will be above, some points will be below. In this case, they're all pretty nicely on that line, so that's okay. Now, B, calculate the gradient of the line of best fit drawn in part A. Show your working, so you know how to do gradients, rise over run. Just pick points that are on the line. So there's a point, I'm going to use that one. And another point I'll use will be maybe that one. Okay, so those points are 20, 2. This point is, what's that, 115, 12. Alright, so gradient equals, okay, what are my numbers again? Rise, 12 minus 2 over run, 115 minus 20. That is going to give me 10 divided by, what's that, 95. 0.11, let's say. I've got to be very, very careful here. I forgot about something I just realized. The units, okay, so that's times 10 to the 10 on top. So I'll just remodify my thing. Good thing I just remembered. That'll be 10 times 10 to the 10 over, and that's 95 times 10 to the 24. Okay, good. So let's quickly change that. So 10e10 divided by 95e24. Cool. 1.1 times 10 to the negative 15. I won't say g, I'll say gradient. Right. 1.1 times 10 to the negative 15. Part C, use the value of the gradient calculated in part B to determine the mass of Saturn. Show your working. Alright, well, let's think about how we're going to do this. What have we got? We've got information about t squared and r cubed. Where have we seen t squared and r cubed before? That was here. R cubed over t squared equals, gm over 4 pi squared, which itself came from the fact that we're in circular motion. So that's the circular motion formula. I'll show you. That is this one. Okay. Also the fact that we are in a gravitational orbit, so that comes from here. So I'm basically combining those two equations together. Alright, now our job is to work out the mass of Saturn. So this thing here, that's not our rise over run, but if I flip everything upside down, I get t squared over r cubed equals gm, 4 pi squared over gm. Alright, now, actually I don't think I need to do that. What did I do that for? I'm a silly duffer. Let's go back one step. Okay, So we have plotted a graph of t squared versus r cubed. Okay, so the y variable, okay, y is t squared, and our x variable equals r cubed. So what we would like is a formula in the form t squared equals something times r cubed, because that's y equals mx, and that's the equation of a straight line, which is what we appear to have. So what stuff has to go here? Well, that's me now rearranging this formula to get it into t squared on its own, and then a bunch of stuff in front of r cubed. Now, that's where I was going with the rearranging before. So if I flip those two fractions, I get t squared over r cubed equals 4 pi squared over gm. And so t squared equals 4 pi squared over gm times r cubed. So this whole thing here should be the value of the gradient of this graph. Okay, so I can just say gradient equals 4 pi squared over gm, which we've already found the gradient up there, 1.1 times 10 to the negative 15. And so therefore m, just doing one last little bit of algebra now, m is going to be 4 pi squared over g times 1.1 times 10 to the negative 15, which when I put all of that into the calculator, what do we get? We get 4 times pi squared over 6.67 times 10 to the negative 11 times 1.1 times 10 to the negative 15. 5.38 times 10 to the 26, that sounds roughly like the mass of Saturn. 5.38 times 10 to the 26. Are we correct? Let's have a look at the report. Here we go. So, let's double check our gradient thing. Yep, so the gradient was fine. Everyone's going to have slightly different lines of best fit. So we are just inside the range, 1.1 times 10 to the negative 15, so that's fine. Now part C, there we go. So they've used that formula. Okay, they've used the upside down version, which sometimes is helpful to have it written down as well. And then we've had to put that into the correct form. Okay, which is what they've done, and then we found the mass of Saturn to be, well, they've got a slightly different value, but it will be consequential on whatever you've answered to part B. Okay, I think that's it. Alright, cool, so we'll stop there. Very long video, this one. I think I've just done a lot of talking, but we'll stop there, and we'll see you later.